Hi everyone, and welcome to the next installment of my Algebra and Pre-Calculus video series. This video is going to be a continuation of the last one. In the last one we discussed division of polynomials and synthetic division. In this one we're going to be talking about zeros of polynomial functions. And this was also something we talked about in the previous video. I just want to do a little bit of a review before we get started. So a zero of a function is a number, let's call it c, right? Some number c, such that f of c is equal to 0. Right? So if you think about a function as an input-output machine, right? A number goes in, a number comes out. Right? If c is a number, right, and we plug that number or evaluate the function at that number, right? So we plug c into the function for x, and the output out pops a 0, then c is called a 0 of f of x. Okay, so we're interested in finding zeros of a function. One way to find zeros of a function is to set up the equation f of x equals 0. So take the function. In this case, our function is going to be a polynomial, but this is not. These are not definitions for polynomial functions. These are definitions for all functions. But for what we're doing right now, polynomials. If you take your polynomial, set it equal to 0, and that equation has solutions, which it always will, we call those solutions roots. So roots and zeros, these two terms, they don't mean exactly the same thing, but they're more or less the same thing. When we're talking about functions, we call them zeros. When we're talking about equations, we call them roots. Now, if c is a 0 of a function, then c is a root of the equation. That function is equal to 0, and vice versa. Moreover, now c doesn't have to be a real number. It could be imaginary. It could be anything, any number, any complex number. But if c is a real number, right, if a 0 of f of x is a real number, then on the graph of the function, it's also going to be an x-intercept. Right, we're not going to be graphing in this video, but it's worth noting this connection between the graphs and the functions and the equation f of x equals 0. So there's a few theorems that we're going to need to work with, all simultaneously. So the first one, let me go to the next slide. The first one is something we've seen before, the zero factor theorem. And if you take two things, multiply them together and get 0, either the first thing's got to be a 0 or the second thing's got to be a 0. We've used this in the past in my previous videos. For example, solving a specific type of polynomial equation. So far, all we've done is quadratic equations. So let's say x squared plus 5x plus 4 is equal to 0. Right, so one method for solving this is to factor and use that factored form to solve. In this case, this quadratic does factor. In this case, it's x plus 4 times x plus 1. And what the zero factor theorem tells us is that we could take each factor individually, set it equal to 0, and solve for x. So here x would be negative 4. That's one root of this equation. So it's 1, 0 of the function f of x equals x squared plus 5x plus 4. The other one would be the other factor. X plus 1 is equal to 0. So this zero factor theorem is really useful because it allows us to start with one equation, right, this one in green, right, and rewrite it as two simpler equations to solve. Right, so this is what the zero factor theorem allows us to do. So we're going to be using this again now in the context of all polynomials, not just degree 2 or quadratic polynomials. All right, we also need a couple of new theorems that we haven't used previously before this topic of polynomials. There's the remainder theorem. Right? The remainder theorem says if you take a polynomial, f of x, and divide it by x minus c. So we're using synthetic division for that. Then the remainder is the same number that you would get if you plug c into the function. Right? The remainder is f of c. So what we're looking for values of c that when we plug them into our function, we get a 0. Right? So what we're actually looking for are numbers, which we're going to use for c down here, that when we divide, we get a remainder of 0. And once we find remainders of 0, then our next theorem, the factor theorem, comes into play. So if we find a 0 of the function, so if f of c is equal to 0, then x minus c is a factor of f of x. Right? So more directly, the factor theorem says if we find a 0, then we have found a factor. Right? If we find a 0 of f of x, let me be more specific, a 0 of f of x, then we have found a factor of f of x. All right, so we're going to be using synthetic division. We used it in the previous video. So if you're still shaky on how synthetic division works, I'm not going to slowly explain it this time around. I'd say go back to my previous video where I explain how synthetic division works. In the last video, I worked through, I think, about 6 problems. And the last problem from the last video, I'll put it up on the screen. Solve the equation x to the third plus 2x to the second minus 5x minus 6 is equal to 0. All right, so this is the question. This is what we need to do. Solve this equation. But we were given an additional piece of information. Given that 2 is a 0 of f of x equals x to the third plus 2x to the second minus 5x minus 6. So what we're basically told here, like what this part that I underlined in red, right, what this means is that if we use synthetic division, so I'll use the coefficients of the polynomial, 1x to the third plus 2x to the second minus 5x minus 6. Right? What this part underlined in red is saying is that if you use the number 2 up here, you will absolutely get a 0 down here. All right, let's just make sure that works out. Bring down the 1. 2 times 1 is 2. Add down, we get 4. 2 times 4 is 8. Add down, we get positive 3. 2 times positive 3 is 6. Add down, check. Yes, we do get 0. The topic of this video is, okay, what if this part was not given to us? What if all we've got is that part highlighted in green? How do we know what number to put up here? How do we know what number to put up there to give us a 0 down here? How do we know what number to choose? Well, unfortunately, there's going to be a little bit of trial and error involved here. We're going to have to try different numbers for C up here. Okay, the first question is, how do you know what numbers to try? There are infinitely many numbers out there. And if you just start picking numbers at random, you could try 100 different numbers and none of them will give you 0 as a remainder. So the last theorem I want to bring up is the one that tells us how to refine our search, right? How to systematically and efficiently test some numbers so that we don't do too much work until we find one that gives us a remainder of 0. Okay, on the next slide is that final theorem that we need to discuss before we could do a couple of problems. And that's the remainder theorem. And so this is going to be the last one. So let f of x be a polynomial with leading coefficient a and constant term b. Let's just make sure we know what that means. Let's just I'll give you an example. Just making up a polynomial at random. Let's say 4x to the fourth power minus 2x squared plus 6x plus 5. All right, here's a polynomial. The a and the b I'm referring to are the first and last numbers, right? So in this case, the leading coefficient, we're going to call that a. So for this example, a would be 4. And the constant term is b, so we'll call this b. B is equal to 5. So this is what I mean by the a and the b, the leading coefficient and the constant term. Okay, so once we know what we're referring to when we say the a and the b, then, and this is the important part here, then the only numbers that could even potentially be zeros of a function must look like this. They must be a factor of the number b divided by a factor of the number a, right? If it doesn't look like this, it's definitely not going to work. It's definitely not going to be a zero of your polynomial. All right, so let's put this into action and do an actual problem. So on the next slide, I've got the first problem. Right? Consider the function f of x. Oop, I meant to use a highlighter there, not a pen. Consider the function f of x equals x to the third power plus 6x to the second minus 34x minus 39. All right, consider this function. What we want to do is find the zeros. Basically, did it again. Find the zeros of f of x. All right, so here's the process. We start with the rational zeros theorem. We start with the rational zeros theorem. So for this function, a, the leading coefficient would be 1, the number in front of the x cubed, and b would be 39, actually negative 39, but it doesn't matter because we have to use positive and negative versions of each number. Okay, so c has to look like some factor of the number 39. So what are all the numbers that divide evenly into 39? Well, I know 1 goes into 39 times. We need the positive and the negative version because our zeros could be negative numbers as well. So 1 goes into 39, negative 1 goes into 39. 3 and negative 3 are factors of 39. 3 times 13 is 39, which means 13, positive and negative, also a factor. And 1 times 39 is 39, so 39 is a factor of 39. Every number is a factor of itself. And then factors of a would be plus or minus 1. All right, so we take every possible combination of numbers. One number from the list on top, which is coming from b, factors of b. One number from the list on the bottom. In this case, it's only a 1 and a negative 1. So I'll just systematically go through the list. I'll start with 1, then I'll do the 3, then the 13, then the 39. So 1 over 1, 1 over negative 1. So that gives us 1 and negative 1. Right? Then we've got 3. 3 over 1, 3 over negative 1. So that's 2 more, positive 3 and negative 3. All right, so we're generating a list of potential candidates here that might be zeros of the polynomial. All right, then we've got 13. So 13 over 1, 13 over negative 1. And finally, 39. 39 over 1, 39 over negative 1. So that's two more numbers, 39 and negative 39. All right, so somewhere on this list is a 0 of the function f of x. If it's not on this list, it is not a 0. If it is on this list, it might be a 0. So what we're going to do is just, at this point, trial and error. So we take the polynomial x to the third plus 6x to the second minus 34x minus 39, and we use synthetic division to divide x minus c, where c, we're going to use each of these numbers here. Hopefully we don't have to go through all 8. But for example, let's try 3. I'm just randomly picking 3. I don't know what the answer is, but hopefully we find it soon. Bring down the 1. 3 times 1 is 3. Add down, we get 9. 3 times 9 is 27. Add down, we get negative 7. 3 times negative 7 is negative 21. That gives us negative 60 as our remainder. So that did not give us a 0 remainder, so we could cross off the 3. That didn't work. All right, let's try, I don't know, positive 1. Same thing, 1, 6, negative 34, negative 39. Again, if you're still shaky on synthetic division, check out my previous video. 1 times 1 is 1. Add down, we get 7. 1 times 7 is 7. Add down, we get negative 27. 1 times negative 27 is negative 27. Add down, we again don't get 0. We get negative 66. So that means 1 is not a 0. So see where I'm going with this? This is involving a little bit of trial and error. Okay, I'm out of room on this slide, so I'm going to go to the next one. I think I have a copy of this problem just to give us a little bit more room to work. All right, so possible zeros, the 1 didn't work, the 3 didn't work. So let me try negative 1. So our coefficients 1, 6, negative 34, and negative 39. Bring down the 1. Negative 1 times 1 is negative 1. Add down, we get 5. Negative 1 times 5 is negative 5. Add down, we get negative 39. This is looking promising. Negative 1 times negative 39 is positive 39. Add down, we get 0. All right, so the number negative 1 is a 0 of this function. Now the factor theorem says if c is a 0, then x minus c is a factor. So what we essentially have done here is we have factored this polynomial. So f of x is equal to x to the third plus 6x to the second minus 34x minus 39, which now becomes x plus 1. Why is it plus 1? Well, c is negative 1, so x minus c is x minus a negative 1. Minus a minus is a plus. So if c is negative 1, then x plus 1 is a factor. x minus c is x minus minus 1, which is x plus 1, right? Erasing the x, that may need a little bit more room down there. And times what? Well, times the quotient, and that's down here. That's the result, right? Quotient, remainder 0. So our quotient is 1, 5, 39, 1, 5, negative 39. So that's 1x squared plus 5x minus 39. All right, so we found 1, 0, which means we found one factor. We've essentially gotten one step closer to fully factored. And now at this point, moving on to part C, use the 0 from part B and a graphing utility. So in this problem, I'm saying, okay, TI-84, maybe you want to use Desmos or some other graphing calculator or online graphing utility to find the remaining zeros of the polynomial function. All right, so we're basically solving this equation. Set this equal to 0. Well, this is quadratic. We already have a formula for finding the zeros of a quadratic function. All right, I'm not going to pull up a calculator on the screen, but if you want to pause it right here and use a calculator or use Desmos, not a bad idea. But we could also use the quadratic formula. We'll get the same answer. So x equals negative b plus or minus the square root of b squared. So I'm using the 1 for A, the 5 for B, the negative 39 for C in the quadratic formula. A equals 1, B equals 5, C equals negative 39. All right, so I'm just taking those three numbers and plugging them in to the quadratic formula. So b squared is 25 minus 4 times A times C, all divided by 2 times A, so that's 2 times 1. All right, so if we take 25 minus 4 times 1 times negative 39. Well, let's see. 4 times 1 is 4. 4 times 39 is 156. Two negatives make a positive, so when we add 25 to that, we'll get 181 under the square root. So these are the other two zeros. These are the other two zeros. So we've got the minus 1, and we've got these two answers over here. Negative 5 plus the square root of 181 over 2, and we've got negative 5 minus the square root of 181 over 2. At this point, if you want to go further, answer part C, put this into a calculator and round it to 3 decimal places. But this is the exact answer. I'm going to stop here. Feel free to pause and convert that to a decimal. All right, let's do one more of these. Same question, different function. All right, consider the function. In this case, we've got f of x equals 7x to the third plus 51x to the second plus 15x plus 7. And we're going to do the same thing. Our possible values of c that will be zeros of this function. Have to be some factor of 7, that's the b, some factor of 7 again, so we have the same number for a and b, so a is 7, also b is 7. So what are the factors of the number 7? Well, plus or minus 1 and plus or minus 7. And then for a, Also plus or minus 1, plus or minus 7. So we take every possible combination, 1 over 1, 1 over negative 1, 7 over 1, 7 over negative 1, 1 over 7, 1 over negative 7. So we just exhaust all possible combinations of numbers. All right, so we're going to get a 1, a negative 1, a 7, a negative 7. What else? 1 over 7, 1 over negative 7. So that's 1/7, and negative 1/7. So again, somewhere on this list has to be that one real zero. Otherwise, we can't solve the problem. Otherwise, we can't solve it. All right, so one of those numbers is going to work. So when we use synthetic division, we got 7 x to the third, 51 x to the second, 15x plus 7. Bring down the 7. And now we got to test some numbers over here. Okay, we're looking for a remainder of 0. So let me try, I don't know, I'll try -1 first. I'm going to start with some whole numbers, and then, hopefully we don't have to deal with the 1/7, the fractions, but let's start with a whole number. -1 times 7 is -7. Add down, we get 44. -1 times 44 is -44. I don't think this one's going to work out. Add down, we get -29. -1 times -29 is 29. Add down, we get 36. That is not 0, so -1 is not a 0 of the function. All right, maybe I'll get lucky on the second try. Let's try -7. All right, so this is the scrap work, right? This is what I'm writing in black. This is, our work off onto the side. We're trying to solve this problem. 7, 51, 15, and 7. Bring down the 7. Okay, so -7 times +7 is -49. Add down, we get 2. Okay, -7 times 2, -14. All right, this is looking good. Add down, we get +1. -7 times +1 is -7. Add down, we get 0. Okay, so -7. -7 is a 0 of this polynomial. So I'll do the same thing as in the previous problem. I'm going to go to the next slide just to free up a little bit more room. Right? -7 was the 0, so that tells us that x plus 7 is a factor of f of x. All right, so we're using our synthetic division. We're using our result from synthetic division. Let me write it out one more time. 7, 51, 15, and 7. I'll just do this one more time quickly. -49, add down is a 2. Multiply, add, multiply, add. All right, so this is our remainder. This is our quotient. So f of x, we started with 7x to the third plus 51x to the second plus 15x plus 7. And because we found 1, 0 of the function, we have factored, at least initially factored one step of f of x, x plus 7 times 7x squared plus 2x plus 1. All right, remember, where this is coming from is the synthetic division. This is from our work over here on the left. 7, 2, 1. All right, 7x squared plus 2x plus 1. Now, this is quadratic, so we can use the quadratic formula. Again, A is 7, B is 2, C is 1. So we've got one answer, right? One of the zeros is -7. The other two are going to come from the quadratic formula. So x is equal to -b plus or minus the square root of b squared, which is 4, minus 4 times a times c. 4 times 7 times 1. So minus 28, all divided by 2 times a, which is 14. So that's -2 plus or minus the square root. Now we get a negative under the square root. So this is an imaginary number. This is an imaginary number. The square root of 24, well, let's see. 24 is 4 times 6, right? So 24 contains a perfect square, 4 times 6, and then the negative sign is going to become an I. So that's going to be 2 times I times the square root of 6. And it looks like we have 3 even numbers here, the -2 and the 2 and the 14. So we could do some canceling there. So that'll be -1 plus or minus I times the square root of 6 divided by 7. So those are the other two zeros. Now, the difference between problem 1 and problem 2, in problem 1, we got 3 answers, 3 real numbers. So if we were to graph number 1, we would see 3 x-intercepts. For problem 2, this one that's on the screen right now, we have 1 real zero, -7, and 2 imaginary zeros. So if we graph this function, something like this is going to happen. Something like this. It's going to hit the x-axis and then not again, right? Just we're only going to get 1 x-intercept at -7. Okay, so first 2 problems, we're looking for zeros of a function. I have 2 more problems I want to do. In the next 2 problems, rather than finding zeros of a function, solve the equation. Right? Find the roots of the equation. Now remember, zeros of a function, roots of an equation, they're not exactly the same thing, but they are very, it's like 4 quarters versus a dollar bill. Right? They mean more or less the same thing. So we're going to find them in the same way. Rational zeros theorem, synthetic division, trial and error, factoring, quadratic formula, if necessary, and we'll go from there. So step 1 is always, right? Starting the problem is sometimes the hardest part, the very first step. How do I start? Well, solving a polynomial equation, this is where you start, the rational zeros theorem. Right? If the degree is higher than 2, if it's quadratic, if the highest power is x squared, we don't need to do any of this. We have a quadratic formula. But if the highest power is 3 or above, if the degree is 3 or above, this is how we start the problem. We come up with a list of possible zeros, or in this case, possible roots. A root is an answer. Right? We're looking for roots, we're looking for answers. Solutions to this equation. All right, so the a is the leading coefficient. We have 1x to the third power, and the b is the constant at the end, so b is 6. So the only values for C that might give us a 0 remainder are going to be some factor of the number 6. So numbers that divide evenly into 6. So 1 goes into 6 times. 2 goes into 6 3 times. 3 goes into 6 2 times. And 6 goes into 6 1 time. A is equal to 1. And the only numbers that divide into 1 evenly are 1 and -1. Okay, so every possible fraction we can make out of these numbers. 1 over 1 is 1. 1 over -1, -1. 2 over 1 is 2. 2 over -1 is -2. 3 over 1 is 3. 3 over -1 is -3. 6 over 1 is 6. And 6 over -1 is -6. So again, somewhere on this list is an answer. It has to be. And again, if there's not, then this problem cannot be solved by this method. So we've got 8 possible answers. We're only guaranteed, I put these problems on here because I know they can be solved. So we are only guaranteed to have 1. So we're looking for that one real root somewhere on this list. So we'll set up synthetic division. 1, -37, 6. Bring down the 1, and we'll test some numbers over here. I don't know, let's start with +3. Okay, now before I write anything else down, you may or may not have noticed the mistake that I just made intentionally, just to make sure everyone's paying attention. There's a problem with this, right? If you look at the original equation, we have 1x to the third, -37x plus 6. So we've got 3 numbers there, 1, -37, and 6. But we can't set up our synthetic division like this. Right? Because if we write it out like this, then we know this is the constant term. This is the x term. And this would be the x squared term. There is no x squared. There's an x cubed. So if there's a missing power of x in your equation or in your function, depending if the problem is asking for roots or zeros, we need to treat this like x to the third plus 0x to the second minus 37x plus 6 is equal to 0, right? We have to take this equation and account for that missing power of x. Because remember, synthetic division is shorthand notation. It uses place value. So if we write 1 and then a -37 and then a 6, that doesn't mean the same thing as the original equation. So we've got to do a 1, a 0, a -37, and a 6. Okay, let's get rid of this. Now we can do our synthetic division. 3 times 1 is 3, add down, we get 3. 3 times 3 is 9, add down, we get -28. 3 times -28 is -84, and 6 and -84 does not give us 0. All right, so 3 does not work. Let me try -1, see if that works. 1, 0, -37, and 6. Bring down the 1. -1 times 1 is -1. Add down, we get -1. Negative times negative is a positive. Add down, -36. Multiply, add. -1 doesn't work. All right, let's try positive 6. 1, 0, negative 37, and 6. Bring down the 1. 6 times 1 is 6. Add down. 6 times 6 is 36. Okay, this is looking good. Add down, we get negative 1. 6 times negative 1 is negative 6, and that gives us a 0 remainder. All right, so we have found one real root. So let me go to the next slide, just we have a little bit more room. I think we found that 6 was a 0, and then our work, again, let me just bring back our synthetic division with the number 6. 1, 0, negative 37, and 6. 6 times 1 is 6. Add down. 6 times 6 is 36. Add down. 6 times negative 1 is negative 6. Add down. Remainder of 0. And then the rest is the quotient. So we start with x to the third minus 37x plus 6 is equal to 0. We found a factor because we found a 0, right? The 0 was 6, so x minus 6 is a factor. The other factor is the quotient, so that's x squared plus 6x minus 1. This is coming from this. 1, 6, negative 1. And so we got one answer so far. X equals 6. Let me circle that in green. That's an answer. The other two answers are coming from that highlighted green quadratic expression. So we set that equal to 0. This is the zero factor theorem. So we could say, well, let's say for the quadratic formula, A is going to be 1, B is going to be 6, C is going to be negative 1. So plug those numbers into the quadratic formula. X equals negative B plus or minus the square root of B squared minus 4 times A times C. So that's going to be a minus 4 all over 2 times A. 36 minus a minus 4 is going to be 40 divided by 2. And let's see, square root of 40. Well, 40 is 4 times 10. So we could take the square root of 4, which is 2, leaving us 10 under the square root. We could factor out and cancel a 2, common factor on top. All right, so those 2's cancel. And we get negative 3 plus or minus the square root of 10. All right, so those are the other two answers, the other two solutions. All right, so we get x equals 6. That's the first answer we found. We found that using synthetic division. Then we've got x equals negative 3 plus the square root of 10, and x equals negative 3 minus the square root of 10, right? The last two, the second and third answers, they came from the quadratic formula. Okay, one more problem. The previous three were third degree polynomials. Let's do one example with something other than a x cubed degree 3 polynomial. So we'll look at the last problem I want to do. Same problem as number 3, just a different equation. So now we've got x to the 4th minus 4x to the 3rd minus 3x to the 2nd plus 16x minus 4 equal to 0. Okay. We start this problem in the same way as problems number 1, 2, and 3. We're going to start with the rational zeros theorem. Come up with a list of possible answers. So we're going to take factors of 4, so plus or minus 1, plus or minus 2, plus or minus 4, divided by, again, factors of 1, because our A is 1, our B is negative 4. So 1 over 1 is 1. 1 over negative 1 is negative 1. 2 over 1 is 2. 2 over negative 1 is negative 2. 4 over 1 is 4, and 4 over negative 1 is negative 4. So we've got 6 potential candidates for roots or solutions to this equation. All right, so we've got 1x to the 4th minus 4x to the 3rd minus 3x to the 2nd plus 16x minus 4, that's our polynomial. And in this case, in this problem, we are actually looking for 2 real roots. 2 real roots. So what that's telling us is 2 of these numbers, we should expect 2 of those numbers on that list of 6, 2 of them to give us a remainder of 0. So let me start with, I don't know, I'll pick 2 at random. Bring down the 1. 2 times 1 is 2. Add down, we get negative 2. 2 times negative 2 is 4. Add down, we get 1. 2 times 1 is 2. Add down, we get 18. Ooh, let me back up. Small sign error here. Let me erase the 18 and the 2 and the 1. Sorry about that. Let's see. Let's go back. 2 times negative 2 is negative 4. Okay, add down. That changes things. Add down, we get negative 7. Okay, yeah, there we go. Now we're back on track. 2 times negative 7 is negative 14. Add down, we get 2. Oh, it's a good thing I caught that mistake. 2 times 2 is 4. Add down, we get 0. Ooh, finally, we got one on the first try. Sometimes you're lucky, sometimes you're not. Okay, so 2 is a 0, which means x minus 2 is a factor. Here's our remainder. Here is our quotient. So the original equation was x to the 4th minus 4x to the 3rd minus 3x to the 2nd plus 16x minus 4 equals 0. We just found one factor. We found 1, 0, which means we found one factor. C is equal to 2, so x minus c, or x minus 2, is a factor. And then the rest, the other factor in this step would be x to the 3rd minus 2x to the 2nd minus 7x plus 2 is equal to 0. All right, so again, this is our quotient. This is coming from synthetic division as well. Right, this is coming from down here. 1, negative 2, negative 7, 2. Okay, 1x cubed minus 2x squared minus 7x plus 2. Okay, so what do we do now? We can't do the same thing as in the previous three problems. We can't use the quadratic formula because this is not quadratic. This is not quadratic. We have to factor this. Now we have to factor this guy. How do we factor an x cubed polynomial? We got to do the whole process over again. Right? Synthetic division, rational zeros theorem. So what we're going to do, treat this like a new problem. But if we look at this list up here of possible values of c that might give us a zero remainder, well, the constant at the end is no longer a 4. Now it's a plus 2. I'm looking right here. Plus 2, not plus 4, which means the 4 and the negative 4 are not going to work. So that's two numbers off our list that are not going to work. Makes things a little bit easier for us to maybe get the right answer on the first guess. All right, so let me go to the next slide to free up a little bit more room. Okay, so the first one we found, the first zero we found was 2. And then we said, okay, 4 and negative 4 are not going to work because the step we're at right now, and let me just bring this over from the last slide, we had x minus 2. And I believe we had x to the third power, negative 2, negative 7, minus 2x squared minus 7x plus 2 is equal to 0. And we're focused right now right here. Right? This original problem, this is where we started. And now we're down here. We were able to factor it. This is not factored completely, but we find one zero, we find one factor. We need to find a second zero, which means a second factor. So let's do synthetic division again, but we're using only this part that we need to factor. Right? We're not going back to the original problem. Right? We find 1, 0. We brought it down from power of 4 to power of 3. Okay, so we've got 1x to the third minus 2x to the second minus 7x plus 2. And let's try, I don't know, let's try a minus 2. Minus 2 times 1 is minus 2. Add down minus 4. Multiply, we get 8. Oh, I think we might have it. Negative 2 times 1 is negative 2. Add down, we get 0. Yes, lucky again. So, positive 2 and negative 2, both are zeros. So that means we've got x minus 2 times x plus 2 times x squared minus 4x plus 1 is equal to 0. So let me do a little bit of color coding here. This came from this and this. All right, the x plus 2 came from our choice of minus 2 for c and the remainder of 0. And then the x squared minus 4x plus 1, this is our quotient. All right, our result from synthetic division. All right, remember, this is the remainder, and this is the quotient. All right, so we've got one solution here. X is equal to 2. Circle it. Done. We've got another answer here. X is equal to negative 2. Circle it. We're done. So now we got x squared minus 4x plus 1 is equal to 0. And again, we have a quadratic formula for this. We no longer need to use synthetic division, and we're not guaranteed to even have two more rational roots. They could be irrational, they could be imaginary. Who knows? So we'll plug this into the quadratic formula. Negative b, that's positive 4, plus or minus the square root of b squared. Negative 4 times negative 4 is 16, minus 4 times a times c. So that's a minus 4 divided by 2 times a. And once we simplify this a little bit, we should be done. We should be done. So we've got 4 plus or minus the square root. 16 minus 4 is 12. The square root of 12. Well, 12 is 4 times 3. The square root of 4 is 2. We still got a 3 under the square root divided by 2. And we can simplify this. If you factor out a 2 on top, that will cancel the 2 on the bottom, and we get 2 plus or minus the square root of 3. So those are the other two solutions, the other two roots of this equation. X is equal to 2 plus the square root of 3. Right, that's one answer. And then the other one, finally, x equals 2 minus the square root of 3. All right, these problems are not short. Right, they're not short. We're no longer in the realm of one-step, two-step problems. Solving polynomial equations. There's a lot of moving parts here. Right, there's a lot of things I've covered in previous videos that are in play here. You have a few new theorems: synthetic division, the factor theorem, the remainder theorem, the rational zeros theorem. What else? The zero factor theorem. There's a lot going on here. So it takes some repetition, going through a handful of problems until this process really starts to click. It's helpful if you sort of write out the steps, not for like the work for a problem. I mean, like, solve a polynomial equation. Step 1, apply rational zeros theorem. Step 2, come up with a list of possible zeros. Step 3, start testing them one at a time with synthetic division. Look for zero remainders, and so on. So it's just like sort of turn this into an algorithm, a step-by-step process that you could follow every time. We just did 4 problems. We just did 4 problems. It was the same sequence of steps in each of those 4 problems. Okay, I'm going to leave it at that. That is the end of this video. I hope this was helpful.